Here we're going to sketch the region whose area is given by an integral and evaluate the integral. The integral is from pi over 2 to pi of the integral from 0 to 2 times the sine of theta of r dr d theta. And we'll note here that f of xy is equal to 1. That's how we're getting area. For our region, looking at the limits on r, we see that r goes from 0 to 2 times the sine of theta, and theta is going to go from pi over 2 to pi. R equals 2 times the sine of theta is going to be a circle of diameter 2 that's symmetric with respect to the line theta equals pi over 2, also known as the y-axis. I have the circle here, and knowing now that theta goes from pi over 2 to pi, we're looking at the portion that's in the second quadrant. As far as the integral goes, I'd like for you to pause the video and see if you can come up with an answer. After integrating r with respect to r, we have the integral from pi over 2 to pi of 1/2 r squared, and we're going to replace r by 2 sine theta and by 0, take the difference using the fundamental theorem of calculus part 2, times d theta, putting 2 times the sine of theta in place of r and then reducing by 1/2 because we have the factor of 1/2, we get the integral from pi over 2 to pi of 2 times the sine squared of theta d theta, because plugging 0 in place of r zeroes out that term. Now we have the sine squared of theta that we need to integrate, and I'll remind you that there exists something called a power reducing formula. The sine squared of theta is equal to 1/2 of the quantity of 1 minus the cosine of 2 theta. We then have the integral of that from pi over 2 to pi d theta. That integrates to theta minus 1/2 sine of 2 theta, evaluated from pi over 2 to pi. Plugging either pi or pi over 2 into theta for the sine of 2 theta will give us 0 each time. We then end up with pi minus pi over 2, so the result is pi over 2. That should make perfect sense because, folks, we were looking at the area of half of a circle of radius 1. Area is pi r squared, half of that, pi over 2. Next up, we are directed to evaluate the integral. It's the double integral over r of the quantity 2x minus y dA by changing the polar coordinates, and r is the region in the first quadrant enclosed by the circle x squared plus y squared equals 4 and the lines x equals 0 and y equals x. I'd like for you to see if you can do this. First, start by drawing the region in the xy plane, and then remember that dA is, I'm not going to say it, see if you can remember it, and then use your conversions and come back when you are done. All right, our region in the xy plane looks like a pizza slice. We're going from the angle theta equals pi over 4 to theta equals pi over 2. That's the first quadrant version there. And we are in a circle of radius 2, so r is going to go from 0 to 2. Those give us our limits of integration. So the double integral over r of 2x minus y dA becomes the integral from pi over 4 to pi over 2 of the integral from 0 to 2 of 2r cosine of theta minus 2r sine of theta times r dr d theta. Note that we can factor out all of the r's and we are left with a function of theta times a function of r, so I'm taking advantage of that. We have the integral from pi over 4 to pi over 2 of the quantity of 2 times the cosine of theta minus the sine of theta d theta times the integral from 0 to 2 of r squared dr. The r goes pretty quickly here. Using the power rule, 1/3 r cubed from 0 to 2 gives us 8/3. That'll be a factor for our final step there. 2 cosine of theta minus sine of theta integrates to 2 sine of theta plus cosine of theta. That's going to be evaluated from pi over 4 to pi over 2. Substituting pi over 2 in place of theta, we get 2. And pi over 4 in place of theta, we get minus the quantity of square root of 2 plus 1 over the square root of 2, but I've distributed the negative here. So we have all of that times our aforementioned 8/3. This simplifies to 16/3 minus 4 times the square root of 2. Ordinarily, I'd say don't rationalize the denominator, but because we have another square root of 2 in our expression, it makes sense to rationalize the denominator, collect like terms, and then distribute to actually clear the fraction.